Okay, today we are going to continue on the last module, module 5. Last week, or the week before last week, we started on this module, the traffic flow theory and shockwave analysis. And we explained the different, we started with the car following models and the theories behind these car following models, and we started with the distance headway, defining basically the distance headway characteristics and distance gap, and we defined also the time headway, okay, and the traffic density as a function of the distance headway between vehicles. So basically the traffic density is 1000 meters divided by the average distance headway in meters per vehicle, and the result will be vehicles per kilometer per lane. Then we went on to have some background on the car following theories, and we mentioned that it started in the early 50s and 60s, and the first pioneers was the work with pipes, okay, then it's followed by Forbes and General Motors family of models. First of all, before we start, we agreed on a notation that the lead vehicle will have the number n, or the notation n, and the following vehicle will have the notation of n plus 1. The speed of the lead vehicle is basically x dot of n t, and the speed of the following vehicles is x n plus 1 dot, and so on. So this slide gives you a summary for the different notations that we will be using throughout this module. Then we moved on to Bibe's theory. Bibe's theory was basically based around the concept of safe distance, and the driver of the following vehicle usually leaves a safe distance to allow for himself or herself to stop the vehicle if there's something happening. So here it says that the following vehicle leaves for every 10 miles, it leaves a vehicle length. So it was based on this, the minimum distance or the minimum spacing the following vehicle will leave is basically the speed of the following vehicle divided by 10 miles per hour, okay, plus vehicle length. Divided for each 10 miles, it leaves a vehicle length. So here we come with the number of tens in the speed multiplied with vehicle length plus vehicle length. If we assume that the vehicle length was 20 feet, okay, then this equation comes down to be d minimum 1.36 multiply the speed of the following vehicle plus 20. Here we have a comparison between Bibe's theory and field observation, and as we can see, the gray area, this is basically the field observations. This area, this is field observation, and that's Bibe theory. And as you can see, it's a little bit not conservative, so it leaves distance almost at the minimum, and here there's a problem with it, and here there's a problem also. So that means the safe headway in reality is much larger than what offered, or what can be determined using Bibe's theory. So that's, you can see it here also. So that led to another concept, which is basically by Forbes. And Forbes his concept was based on delta T, okay, which is the reaction time, plus the vehicle length divided by the speed of the lead vehicle. So that was the minimum headway. And based on this equation, the work of Forbes, we can get, here that, but again, it's a linear relationship, and as you can see, at low speeds, it underestimates the safe distance, but for the rest, it's almost there. But also at high speeds, it's kind of, short from what's observed in reality. So that led us to the General Motors GM family of models. It's basically, that was a breakthrough. It was based on response. The response of the following vehicle is function of two things. It's function of stimuli and sensitivity. Stimuli is basically measured with the difference in speed. So if the speed of the lead vehicle drops, okay, that means the delta will be negative. That means the response will be deceleration, negative acceleration. And the sensitivity, this is how far, the strength of the response. So the sensitivity was dependent on several aspects, and actually all the different models will be function of different treatment for sensitivity, as you will see now. So that was the first model, that the acceleration of the following vehicle at time t plus delta t, that's the reaction time, equal alpha multiplied with the difference in speed. Alpha is basically the sensitivity factor. From the field, they were able to get different values for reaction times and alphas. And the reaction time was as minimum as 1, and it was as long as 2.2 seconds. Regarding the sensitivity, it ranged from 0.17 to 0.74, and that was the average observed value. As you can see, it's a wide range of values. So they came up with the second model, which was basically using either alpha 1 or alpha 2 extreme points, okay? But again, delta, that was a reaction time, and it was controversial, okay, which alpha to use, the lower bound or the upper bound, and when to use it, okay, which led to the third model. The third model, they discovered that there was a linear relationship between the factor alpha and the spacing between the vehicles, okay, but or on the inverse of the spacing. So that means if the spacing was high, the sensitivity was low. If the spacing was low, the sensitivity was high, and that makes sense. So they came up with this term for sensitivity, which is alpha node. That's basically the slope of this relationship, of this line, divided by the distance between the lead vehicle and the following vehicle. So that was this, basically this model we showed before, that we can integrate it and come from this model to the Greenberg macroscopic flow model. Then they came up with the fourth model, which was basically in this shape. It was, it took into consideration also the speed, not only just the distance or the spacing between the lead vehicle and the following vehicle, but it took into consideration as well the speed of the following vehicle. Okay, then they concluded with the general model. The general model was basically similar to to the fourth model, but it has powers m and l for this term and this term. And based on the value of m and l, you can get into whatever model you want. You can get from model 1 to model 4 easily using this terminology. So actually these values could be used to calibrate whatever model you want or you use in your study. Okay, so that was a brief review for the car following theories and the different models that we have. Now we started with the shockwave analysis. And before we start, we need to understand that there are several relationships between speed and density. The first relationship was linear, as you can see here. That was the green shield model. Then was the Greenberg model, okay, which is nonlinear, and there's the Underwood, exponential model like this one, okay. However, for simplicity, we will use the green shield model because it's linear, and it says that at maximum density the speed is 0, at maximum speed the density is 0, and that's very simple. And that the density or the speed varies linearly with the density, and that was the function that was proposed, or that's the shape of the function that was proposed for green shield model. Any questions so far? Based on the green shield model, we can find the flow density relationship, because basically flow density, if we say, okay, let me just clear this from the board. If we say that Q equal V multiply K, and we said before that V equal VF multiply 1 minus K over K jam. If we multiply it by K, then this becomes, we remove it from here, this becomes K square, and there is K, okay. So as you can see that Q equal VF multiply K minus K square over K jam. That's a parabola. It's nonlinear. Okay. So if we want to determine the maximum flow rate, okay, then we need to find dq by dk. It must equal 0. So if we solve it for this, we will find that at Q maximum, K maximum corresponds to K jam over 2, and V maximum, the speed at maximum flow rate will be VF over 2. That means Q maximum equal VF multiply K jam divided by 4. Any questions so far? And we showed this relationship here, and that was the derivation for that. Here also we showed that the relationship between speed and capacity. So at free flow speed, the flow is 0, and as the flow starts increasing, the speed starts dropping until it reaches to this point. After that, the speed and the capacity both start dropping. This is the congested flow, and this is the stable flow. Now we move to shockwave analysis. What do we mean with shockwave? Basically, shockwave is a line, okay, defining two different states of flow. واضح يا شباب؟ يعني if we have a flow condition and there is another flow condition here, This line is called a shockwave. Okay, if this wave is going forward or backward or stationary, okay, that defines the attribute of this shockwave. Okay, so basically shockwave is a boundary between two states of traffic flow condition. So here is defined: flow speed, density, states change over space and time. When these changes of state occur at a boundary is established that demarks the time-space domain of one flow state from another. This boundary is referred to as shock wave. Okay. In some situations, the shock wave can be very mild, okay, like a platoon of high-speed vehicles, and might be very, observable and very significant, especially at traffic lights. Okay, types of shock waves. Okay, the types of shock waves are there are several types. There's frontal stationary. Okay, there is backward forming, there is forward recovery, there is rear stationary, there is backward recovery, and there is forward forming. Here we can see an example. At the traffic light, as you can see here, how many states of flow do we have? This is the state A, which is the normal flow. This is state A. Okay. Then, once the vehicles arrives here, okay, they start stopping and stacking, after each other. So that's A, they go to B. Okay, so now we have two states of flow, A and B, and there's a line between the cars that are stopping and the cars that are arriving. The speed of this line, how does it progress? This is the shock wave AB. So this is the vector or the shock wave AB. Again, when the signal turns green, vehicles standing in the queue start moving. Okay, so you can see that it's changing state from B to C. Okay, so at this point, this change from B to C, that's saturation here. So it goes this way. So this wave is omega BC. That's the speed of the wave, okay, in this direction. There is a movement, wave of movement starting from the traffic signal and moving down, moving upstream in the queue. Okay, so again, that's another shock wave, which we call it backward recovery. The first wave, that was backward forming, which is basically building up a queue. The one right at the stop line of the signal, that's frontal stationary. There's two states of flow. There is state B and there is state D. Where is state D? That's state D. It's zero flow and zero density. State B, zero flow but maximum density, jam density. You get that, guys? Okay. Here another example for a shock wave. In this example, we have a truck that is entering a road or a single lane, for example. It's entering from here, then it's going exiting again from here. So this truck is going at a slow speed. That means the vehicles driving behind that truck needs to slow down. Okay, so let me just draw this in a better format. If we draw here the speed, the density, flow density diagram, so here we have density and here we have Q, and the current state is here, A. That's the current flow. But when the truck enters, it drives at slower speed. So the slower speed is going to be somewhere here. Okay, so here we will have this wave, okay, going backward at a lower speed, as you can see here. So this is case B. Okay, once it exits, then the flow will go from B to C. There's another wave start forming here. So this is omega BC. As you can see, this one is forward forming according to this figure, but in our case it's going to be backward forming. Okay, here it's backward recovery. There is a shock wave going backward. Okay, so here we have also the same, and here we have from B to D. Okay, there is this wave, that's D. There is no flow here and there is no density, so this is omega BD. Okay, as you can see, there are different shapes, different forms, and different utilization for this shock wave analysis. Any questions so far? Okay, now how do we calculate the speed of this wave? As we mentioned before, the speed of this wave can be determined simply if we have two streams, or if we have two states, like in this case. The speed of the wave, omega AB, is simply the difference of flow divided by the difference in density between the two states. Simple. So omega AB equal QA minus QB divided by KA minus KB. That's it. Okay. Here, that was an example, and the example used the following: the flow density diagram and combinations of the four flow states A, B, C, D. I think we solved this example before last week, correct? شباب.
لا يا دكتور ما خذنا.
احنا ما حليناش الاكزامبل ده قبل كده.
الا اللي قلنا فيها.
No problem, we can solve it again, no problem. That's all right. Okay, what was the requirement here? The requirement was basically to calculate okay, the flow density diagram and the combination of the four flow states in the shown figure. Draw a distance time diagram showing shock wave and vehicular trajectory that results in the following type of shock waves: A, frontal stationary, B, backward forming. Okay, backward forming, it can be from state B to state D. Okay, frontal stationary can be from state A to or actually can be from B to C. That's frontal stationary. Why? Because B and C, the flow is the same. معايا يا شباب؟ ده هنا الفلو تبع A, B, C and D. تمام؟ ف let me just take these out.
دكتور وائل.
Yes.
السكرين على على السلايد.
sorry. مش تقول يا أخي. أنا نقلت دي هنا وعمال أتكلم أنا مع نفسي. Now you are seeing the example?
Yes.
So we start first with A, frontal stationary. Frontal stationary, that means you know, the shock wave is not changing. It's not moving forward or backward, but it's separating between two flow conditions. In order for a stationary frontal stationary, okay, that means omega will equal 0. السبيد دي بتبقى 0. طيب معناها ايه؟ معناها ان دلتا Q على دلتا K must equal 0. صح؟ طيب يبقى اكيد دلتا Q should equal 0, لان if we divide by delta K, if delta K is 0, then if we divide, this is going to be infinity. Correct? So where do we can we get delta Q equal 0? Out of here we have Q A equal 1440, Q B 960, and all these are vehicle per hour, and QC equal 960 vehicle per hour, and QD equal 600 vehicle per hour. Correct? So where can we get different flow, okay, such that the Q equal 0? So it's omega BC equal 0, equal delta Q by delta K equal 0, because it has the same flow rate. So that was basically omega BC. That's the first requirement. A, frontal stationary. واضح يا شباب؟ تمام؟ Let's go to backward forming. Backward forming, that means backward forming. Backward forming, then we need to have a flow higher, then it increase in density, and so AD can be a backward forming. Also AC can be a backward forming. Okay, but we will do just AD. Okay, so omega AD equal QA minus QD over KA minus KD. Actually, we need to calculate all of these values. So forward recovery, it could be from D to B. For example, okay. Rear stationary, I'm not sure, but it could be from C to B. Okay. E, backward recovery. Okay, it could be from C to A. F, forward forming, this could be forward forming, omega AB. Okay, so these are examples. Now we want to have a look at it from here. Let's say repeat the problem with numerical solutions. Assume that the flow density diagram is based on a linear green shield model where U equal 80 plus minus 0.75 K and okay. So let's now convert this into flow density diagram. So we have here, that's K and that's V. Okay, so what is VF based on this equation? We have V equal 80 minus 0.75 K. Okay, so if K equals 0, V equal VF, correct? So it equals 80. So this one is 80. Okay, what if V equals 0? Then K equal K jam. So 0 equal 80 minus 0.75 times K jam. That means K jam, the jam density, equals how much, ya shabab? 80 divided by 0.75, which is basically 4 multiply 80 divided by 3, 106.7. And this is vehicle per kilometer per lane. And this is kilometer per hour. So the jam density 106.7, and here this is the speed. Okay, good. Now we want to calculate the density at QA and density at C, density at B, and density at D. Okay, so in order to do that, let's do the following. What is K? Q, I'm sorry. Q equal K multiply V. So if we multiply speed by K, so we have 80 minus 80 multiply K, that's the speed. Okay, let me just take this. Here is K, multiply the speed. The speed is basically 80 minus 0.75 multiply K. So Q equal 80k minus 0.75k square. Let's take these values to the other side. So we have 0.75k square minus 80k plus q equals 0. Then we can solve and get the k's. So k 1 or 2 equal minus b plus or minus square root of b square minus 4ac divided by 2a. Correct? Correct يا شباب ولا في حاجة غلط؟ So we have k1 equal minus b, which is 80. I'm going to start with the minus square root of 80 square minus 4 multiply 0.75 multiply q divided by 2 multiply 0.75. And once we put this minus and once we put this plus. So KA equal 80 plus is going to be minus, and I'm going to tell you why it's minus. Just try to solve it plus or minus. And here we have 80 square minus 4 multiply 0.75 multiply QA. QA, how much was? QA 1440 divided by 2 multiply 0.75, which is 1.5. كام يا شباب؟
$22.9.
22.9, and the units? Vehicle per kilometer per lane. So that's the first value, or that's the second value. What's the first value? I'm going to tell you, it's 102.9. صح؟
83.7.
Hmm?
83.7.
83.7?
Yes.
Are you sure about this?
Same, doctor, 83.7.
Okay, 83.7. Okay, in our case, which one should we take? Should we take this one or this one? Let's look carefully here. Here, at that flow at QA, look carefully. At the same flow, we have two values of density. We have KA1 and KA2. This one is uncongested. This one is congested. The congested level or threshold is here. That's K jam over 2. What was K jam here? K jam was 106.7. So 106.7 divided by 2, that's going to be 53.33. Correct? So here we are below K jam over 2. So that's the case that we have here, uncongested. So in our answer will be this is the value for KA. واضح يا شباب؟ واضح ولا مش واضح؟ عبد الله.
هذا
كي بي هتساوي 80 plus or minus square root 480 square minus 4 multiplied 0.275 multiplied 960 divided by 1.5 equal خلوا بالكم دي هنا كي بي وكي سي برضه because the flow is the same. So how much is the value?
92.8.
92.8. And what's the smaller value?
13.7.
13.7. Here vehicle per kilometer per lane, and here vehicle per kilometer per lane. Just bear with me. Now, which one is which? Which one is for B and which one is for C? Let's look again. That's B, that's flow state B, and that's flow state C. Which one is going to be, which one is going to be the density for C? KB equal 13.7 vehicle per kilometer per hour, and KC equal 92.8 vehicle per kilometer per hour, because C, that was the state that is congested, B, the state that is uncongested. Clear? Okay. Now we want to find the density for D, and the flow for D, it was 600. K D equal 80 plus or minus 80 square minus 4 multiply 0.75 multiply 600. How much? Sorry.
$8.11.
8.11 vehicle per kilometer per lane, and
98.5.
98.5.
0.5.
Mumtaz. Excellent. Now let's look at the graph here and say, which one shall we take? Out of these values. Shall we take this one or we take this one? I'm waiting for an answer. في درجة اللي هيجاوب. شباب.
Again, did so?
Okay, which value for the which the density value for state of D should we take? 8.11 vehicle per kilometer per lane or 98.5 vehicle per kilometer per lane. And here the state on the curve. Here is D. So which one should we take?
8.11.
Hmm?
8.11.
Good. Who is speaking?
خالد.
Khalid Al-Ataibi.
Yes.
Okay. Why يا خالد؟
لأن الدنسيتي في الجراف أقرب لل 8.11
Okay. Where did you see that?
حسب الصورة اللي أنت وضحت لي دكتور.
Okay. Here is the density. Here is the flow. Okay. So where is how were you you were able to say that it was close to 8? Here is K jam. Here K equals 0. Here is KD. واضح؟
كي جي كم قيمته يا دكتور؟
106.
لا أقرب أجل إلى دي ل 98.
تمام، برافو عليك. لان هو هنا انت فاكر احنا كنا بنقول هنا ده uncongested وده congested، صح؟
صح.
هو اصلا دي في الكونجستد سايد، فالدنس بتاعتها عاليه. واضح؟ زي ما كان عندنا بي وسي الاثنين على نفس الليفل في الفلو، بس واحد في حاله دنسيتي خفيفه جدا وهنا في حاله دنسيتي عاليه جدا، بس الاثنين they result in the same flow. واضح؟ مفهوم
واضح
للجميع
دكتور.
يا شباب؟ مفهوم؟ يبقى انا هنا في الحاله بتاعتنا في الكي دي هي الايه؟ الدنس بتاعتي. اي سؤال، اي استفسار؟ اوكي، let's have a pause now. طيب دلوقتي ناخد example تاني. Now we have another example. Calculate the Q length for the shown traffic signal. Sorry. And estimate the total stop delay per cycle. Okay. Let's assume that we have, that's the intersection here. And that's the traffic light. That's where it turns red. So the vehicles are just traveling through. When it turns red, queues start forming. Okay, so we have a queue that built up to this shape. Then when it turns green, vehicle starts moving. That's during the green phase. And that's the start of the red time here. So the vehicles so where do we have a stop delay? This area is the stop delay. If the red time was R and the flow here, that's QA, that's A, and this state is B and this state is C. If VF equal 80 kilometers per hour, Kjam equal 120 vehicle per kilometer per lane. Okay, these are given, and QA equal say 600 vehicle per hour per lane. Make it 800. Okay, let me just make a quick calculation. Okay, so solution. First we need to determine, let's look carefully at this triangle. We have this triangle. We need to calculate the area of this triangle. So we need to calculate the height of this triangle or this length, and we need to calculate this time. So if we draw this, okay, before we draw this, we just need to define these different states as following. That's the state A, that's the state B, and that's the state C, saturation. So we have first wave omega AB, which is here. That's the first shock wave we have. Then we have a second shock wave, which is between B and C. Omega BC. Okay? So we need to calculate these waves first. So let's, do our homework and calculate the KA and the different, okay. For QA equal 800, so it equal VA multiply KA. Okay, what is the relationship for, we are assuming green shield model, linear model. So in this case, we have that's Kjam, and that's VF, and VF, the free flow. So at any density, we can say that VA, and that's KA. So VA equal V minus, by similarity of triangles, okay, we have VA over VF. The relationship between VA and VF similar to the relationship between this height to this height. So it's basically Kjam minus KA divided by Kjam. So in other words, we can say that VA equal VF multiply 1 minus KA over K jam. As simple as that. So VA equal VF, which is basically 80 kilometers per hour, as we mentioned, and KJM 120. So let's substitute it here. So here we have 80 minus 80 over 120 times KA. So this will be 80 minus 0.75 KA. Correct? No, actually it's 0.67. Okay, so I'm sorry. So we have 800 equal VA times KA, so we have 80 KA minus 0.67 KA square. So it's 0.67 KA square minus 80 KA plus 800 equal 0. So from here we can come up with KA equal 80 plus or minus square root to 80 square minus 4 multiply 800 multiply 0.67 divided by 2 multiply 0.67. So KA equals شباب
108 هذه بالموجب.
108 and
وبالماينس 11.
12 صح
11 بالضبط.
11 يبقى هنا 109 المفروض صح
هي 108.3 ف
108.3 يبقى هنا يبقى 11.7 because if you add both you must end up with 120 vehicle per kilometer per lane. Okay, now we are going to take only the 11 because you know the arrival rate is not congested. Okay, so basically KA is not congested, so we're going to take 11.7 okay vehicle per kilometer per lane. So that's the density at KA. Now for B, KB equal KJAM equal 120 vehicles per kilometers per lane, and QB or QB equal 0. C for the state of C. State of C, that's the saturation case. That's the maximum here. So QC equal Q maximum. Q maximum, according to the, if we are taking a green shield linear speed density relationship, so it will be VF multiply K jam divided by 4. So it will be 2400 vehicle per hour per lane. طيب K C here, how much will be the KC? It's K jam over 2. يعني هتساوي 120 على 2 هتساوي 60 vehicle per kilometer per lane. Now we have all what we need. We have the flows and the densities for different states. Now let's calculate the shock waves for different states. So we have omega AB equal QA minus QB divided by KA minus KB. So here we have 800 minus 0 divided by KA is 11.7 minus KB, that's jam density, 120. So how much is the result here?
minus 7.38.
Perfect. Minus 7.38. What is the units?
So the vehicle per lane
It's a speed.
speed. Sorry.
Okay.
But how is
Just-
it by minus, دكتور؟ كيف جت بالماينس؟
Okay. I will tell you now. But let's just focus on the units.
Meter
It's
per
gonna be
second.
no, there is no second here. It's kilometers per hour. Why?
Okay.
Let's focus. The flow rate is what? Vehicle per hour per lane. Divided by vehicle per kilometer per lane. So the vehicle goes with the vehicle. The lane goes with the lane. But here, divided by. So this will be kilometer per hour. This will go down. This will go up. واضح يا شباب؟ مفهوم؟ That's how the units ended up to be this way. طيب. Sanad, you mentioned something. How come it's in negative? Correct?
Yes.
Okay. Negative means it's propagating backward. And this is what happens. Okay? When the traffic light turns red, vehicles start arriving and stopping. And there is a queue start progressing backward. صح?
صحيح.
That means that's the intersection. When it turns red, first car arrive, second car arrive, third car, fourth car. So there is a state of stopping car progressing backward. The speed of this progression is minus 7.38. Clear? Good. Now, we want to see the omega BC. That's when the traffic signal turns green. Okay, we have a queue of vehicles. The first car start moving, second car, third car. So another wave of movement start progressing in that shock wave. Okay, it's going to be negative, by the way. So, but it's recovering. They are changing from being stopped Okay, from being in that state to being in a state of motion again. So omega BC is basically QB minus QC divided by KB minus KC. So QB is 0 minus QC is 2400 divided by KB, which is jam density, KC jam density over 4 over 2. So here it's 60. So this will be minus 40 kilometers per hour. Correct? So now we have
Yes.
2 shock waves. Now we want to calculate, okay, how, the length of the Q, this L. We want to calculate. So let's take just on the side here, this diagram. So this height, it's L. And the distance from this point to this point, we are going to give it a time T. And that's the red time. So L, okay, here omega B C, and here omega A B. L equals omega BC multiply T. After time T, this moving or recovering wave will get to the end of the Q. Also, the maximum length of the Q will be generated L equal omega AB multiply R plus T. If we multiply this speed by the red time plus this time T, we get L. So we can say that both are equal because L can calculate it this way. So we have omega BC multiply T equal omega AB multiply R plus T. From here we can get T equal how much? Omega AB multiply R divided by how much? Omega BC minus omega AB. So L, the length of the Q, equal omega BC multiply T. So L, just multiply this T by omega BC. So it's omega BC multiply omega AB multiply R divided by omega BC minus omega AB. So that's the length of the Q. That's the number of vehicles in the queue. Okay, so now what can we see from this equation? Now we're going to look at it and just examine it as engineers, not as mathematicians. We are not mathematicians. شباب the more red time we have, the longer the queues we have. يعني كل ما الضوء الأحمر زاد كل ما الايه المثلث ده يزيد. واضح؟ يعني كل ما السايكل تايم زاد كل ما اللينث بتاع الكيوز زاد. مفهوم يا شباب؟ طيب let's calculate if we say that we have a read time. طيب عاوزين نحسب الستوب. اوكي، الافريج او التوتال ستوب ديلي في الحاله دي هيبقى كام؟ يبقى مساحه المثلث ده يا شباب تمام. let's just do this for the time being. if r equal 60 second, L equal how much؟ تمام. يبقى let's do this. L equal omega BC times omega AB. Here we have omega AB 7.38 and 40. So we have 7.38 multiply 40 multiply 60 second divided by omega BC, which is the 40, minus 7.38. Are we correct this way or we have something wrong?
الماينس دكتور حق 7.38.
That's omega AB. Okay.
بس القيمة مطلعينها احنا في
Okay,
الماينس.
okay. Here we are using the absolute values.
اوكي تمام.
Okay. Okay, that's a good point. So we are using the absolute values. Is there anything wrong? There is something seriously wrong. Here these are speeds in kilometers per hour, and here we have the time in seconds. So this must be divided by 3600. Now calculate it.
زيرو بوينت 15.
0.151. So what is the units here? Kilometer. That means the Q length will be 151 كام meters.
5 meter.
Okay. That means if we increase the read time more than this is going to be, if we double the read time, the Q length will double. What about the delay? If we assume that we have a green the green time, green equals 30 seconds. So we have a cycle time of how much? 90 seconds. That's the cycle time. Okay? So how many vehicles are arriving? Okay, let's calculate now the average stop delay per vehicle. How many vehicles arriving? Number of vehicles arriving in cycle. هتساوي Q multiply cycle length. So Q equal 800 vehicles per hour multiply 90 divided by 3600. How much?
20.
في 90 divided by 3600. So that's 20 vehicles per cycle. Okay, let's calculate now the stop delay. Per cycle. The stop delay, which is basically the number of vehicles standing in this queue, okay, the area of this triangle. What's the area of this triangle? It's half L times R. Correct? Correct يا شباب ولا مش correct? What is L? Half L, which is omega BC times omega AB times R. R multiplied by R, this is R square divided by omega BC minus omega AB. Okay? Divided by, this will be in seconds, correct? Or what that would be in what? This is meter. So we need to divide it by K jam to convert it into time per vehicle. So here will be 151 multiplied by 60 divided by K jam, which is 120. So the units will be now how much? 60 multiplied 151 divided by 120. So this is, I'm sorry, this is half here, divided by 2. So this is
37.7.
37.75 second. Okay, let's just review it. Here, this is meter. Here, this is second. Here, this is vehicle per meter. So here, 37.75 second per vehicle. Correct? Okay, so that's the average control delay per vehicle for those stopping. Okay, so if we convert this into vehicles, 151 divided by 120, I'm sorry. Okay, I'm sorry. We are doing something seriously wrong here. 151 multiply. We have 1000. I'm sorry. We have density equal 120 vehicle per kilometer per lane. Okay, this value, there is something wrong here, by the way. It's not 120 vehicle per meter. No, this is wrong. So this, just omit it. I'm gonna go back to this. So this 120 vehicle per kilometer, that means it's 120 divided by 1000. So this will be 120 divided by 1000. it's 0.12 vehicle per meter. Or in other words, if we flip it, so it's 8.33 meter per vehicle. So this is 151. If we divide it by 8.33, so the queue length is 18 vehicles. Okay, so here we can calculate the average delay per those 18 vehicles to be this way: half times 18 times R. So it's half times 18 times 60. So that's the total stop delay. 0.5 multiply 18 multiply 60. So that's 540 second vehicles. Okay, so the average delay per cycle هيساوي التوتال stop delay divided by number of vehicles in the cycle. يعني هنشوف دلوقتي يا شباب، ده عدد او ده فترة الزمن اللي السيارات وقفتها، تمام، كلها. خلاص، هنقسم الرقم ده 540 على عدد السيارات اللي بتصل في السايكل اللي هي كيو في السي. في كل سايكل عندي 20 سيارة، يبقى على 20، يبقى هنا ده المتوسط على 20 يبقى 27 second per vehicle. ده الافريج ستوب ديلي. طيب لو احنا بقى غيرنا if we change just double the times, we are going to use a cycle length double this. If the cycle equal مش 90، لا، بدل ما كانت 90 هنا بقت 180، والريد تايم هيبقى الدبل، بدل ما هو كان 60 هيبقى 120، والجرين هيبقى بدل ما هو كان 30 هيبقى 60. Almost the same ratios, but the cycle time is now doubled and the read time is doubled. Okay, let's see how this will affect our results. First of all, L will be 2L double. So here we will have 18 vehicle multiply 2. Here we will have 36 vehicle. As you can see here, it's the read time multiplied by 2. Okay, number of vehicles per cycle. Number of vehicles per cycle هيساوي كام؟ هيساوي 800 multiply 180 divided by 3600. 800 multiply 180 divided by 3600. So we have 40 vehicle per cycle. طيب التوتال ستوب ديلي هيبقى كام يا شباب؟ هيبقى نفس اللي احنا حسبناه، هاف ال في الار الجديده. يبقى انا عندي هاف ال الجديده بتاعتنا اهي، يبقى هاف في 36 في الريد تايم الجديد 120. يبقى انا عندي 36 في 120 على 2. اوكي، هيبقى هنا 2160 second vehicle. يبقى الافريج ديلي اوكي بير سايكل او بير فيهيكل ان ذا سايكل سوري هيساوي كام؟ التوتال ستوب ديلي اللي هو 2160 على عدد السيارات اللي في السايكل اللي هو 40 divide this by 40 54 second per vehicle. لاحظ احنا ما غيرناش حاجة يا شباب، احنا كل اللي غيرناه الجرين تايم ريشيو the same، الفلو the same، الترافيك density the same، everything is the same. But what we did, we used just longer cycle length. What was the result? We doubled the cycle length, we doubled the delay. واضح؟ You get the point? And we doubled the queue length, as you can see. مفهوم؟ That's why we recommend not to use longer cycle lengths. Most of our problems here in Dammam and in the Eastern Province is basically in the long cycle length. So you see, we could achieve under the same condition half the delay if we use shorter cycle lengths. مفهوم يا شباب؟ Any questions so far?